I'm going to continue today, but it touches two what I think are more advanced topics, and they're also unpublished. The two topics I'm going to cover with you involve using variance, really, and covariance as signatures of neural computation in order to bring out aspects of the features of the neurophysiology that are not immediately apparent when one averages the firing rate, and how the brain integrates prior knowledge about outcomes with a stream of incoming evidence. Now, most of you I know were at the lecture on Tuesday, so very quickly I will just remind you of the basics, and that is that we study decision making in rhesus monkeys that are trained to make decisions about things they see on a video display, and these experiments I'm going to talk about today are the ones that are based on judgments of motion, where a monkey looks at a fixation point, sees a couple of choice targets, and decides whether the net direction of this motion is to the right or to the left. And once again, we vary the difficulty of this task by controlling the probability that a dot plotted at time t will be displaced in motion 40 milliseconds later, as opposed to randomly replaced as part of the noise background. And I'll call that the strength of motion, or the percent coherence. And in the experiments we're going to talk about today, the animal controls the viewing duration by breaking fixation whenever he's ready and making an eye movement. And that allows us to measure both his choice, in this case he chooses right, and his reaction time, the amount of time that elapses from onset of that motion to the beginning of the monkey's eye movement response. And as I told you yesterday, Tuesday, if we record from neurons in the association cortex of the parietal lobe, in particular this area LIP, the lateral intraparietal area, that we find many neurons there that are sort of poised to take the evidence from vision and convert it through a kind of a deliberative, slow, prolonged phase into a plan to answer left or right by making an eye movement. These neurons in LIP are connected to the oculomotor structures. In fact, Richard Anderson identified this area as the part of Brodmann's area 7 that projects to the frontal eye field and the superior colliculus. Okay. And to remind you, these neurons have an interesting feature, that is, they have persistent activity. If we flash a target in the visual field, part of the field that we call the response field, the neuron has this interesting persistent activity. Let's listen to the neuron again. Okay, these are fun neurons to record from. You know, they're not subtle. They have this long, elevated discharge. Here, a discharge while the monkey's waiting for the cue to make an eye movement to the remembered location of that briefly flashed target. And, you know, they're spatially selective. So there's a decrease in the response when the monkey was instructed to make an eye movement outside the response field. And we exploit this property of these neurons, the persistent activity, the fact that they do not need to be continuously fed by momentary evidence from the world in order to respond. That is, they kind of confer what I call the freedom from immediacy, the ability to compute in a time frame not governed by immediate change in the world or the need to control body musculature in real time. It's this capacity that we exploit to study decision making. Okay? So these aren't the neurons that make decisions. They're not the only neurons in the brain that do this kind of thing. In fact, this is a pretty common property of neurons in the association cortex. But these neurons give us insight into the computations. And I told you that what we think is going on based on recording the neural firing rate as a function of time is something like the integration over time of a stream of evidence coming in. Here supporting rightward, that is the eye movement to the response field, and here going against it, supporting the opposite choice. And the real evidence that we have, our evidence, not the monkey's evidence, but our evidence that these neurons are doing something more interesting than planning eye movements is that the rate of rise and the rate of decline is dependent on the strength of the visual motion. So these different colors represent strong motion, intermediate, weak motion. We get all these different kinds of motion. Okay? And I also pointed out that at the end of a trial, when the monkey's ready with his answer, the responses seem to come together just before the monkey makes an eye movement. And that's a sign that maybe some kind of threshold or bound terminates the decision process. Okay? And I didn't show you this graph, but I think it's pretty revealing. If you regroup the trials, and instead of showing you them grouped by motion strength, I show you them grouped by reaction time. These are the long reaction time trials. These are the short reaction time trials, and the ones in between. You really do get the impression that the variance of the response has sort of reached a minimum about 80 to 100 milliseconds before the eyes move. Okay? So that's why we think there's such a thing as a bound. Okay? Now, we don't know where the bound is detected. We don't know how it's set. There's a million things we don't understand about this process. But one thing is for sure is that this basic framework of accumulation of momentary evidence in time until a critical level is reached does a very good job of explaining the monkey's behavior. And I showed you this graph also on Tuesday. That is that if we look at the monkey's reaction time as a function of motion strength and we fit the observations, which are these points, with a smooth curve that is a fit to the first passage times of this random walk to bound, with really only two important degrees of freedom. One, k, that converts motion strength to signal to noise, roughly. The students now know that that's a special root of a moment-generating function. Good enough. And b, the bound height that effectively instantiates the trade-off between speed and accuracy. Then what we see is that we can account for these data, but more impressively, we've used up our degrees of freedom to explain the choices, because by hypothesis, this mechanism couples reaction time to the choice that's made, and we are in this unusual position to predict the monkey's accuracy as a function of, say, motion strength. So we predict he's perfect here, tending to chance at exactly this rate, and that is in fact what we see in the data. Okay, so we think about this kind of a mechanism as explaining these responses, because we think of these responses as the conditionalized averages. Conditionalized meaning that although it may be, consider these blue curves in the middle where we showed the monkey net no direction of motion. It's pure noise. The monkey's classifying. And so on average, we expect Brownian motion that on average is flat. But the trials that end in rightward choices will have some upward drift, and the trials that end in downward choices will have some downward drift. In this case, kind of a meandering. And the reason we think it's a meandering ultimately is because we don't really believe that there's just one mechanism with a bound up here and a bound up here, but rather a race between a mechanism that accumulates right minus left against a mechanism that accumulates left minus right. So these responses are sort of caught, so to speak. They're interrupted by a process we're not measuring, right? There are neurons on the other side of the brain that are terminating the decisions in favor of this target. We're recording from the neurons that are terminating the decisions in favor of this target. Okay, so, and the nice thing about this race is that it generalizes quite nicely to decisions among more than two choices. We've gone out to 4, which is not terribly impressive, but it's nice to see that the same basic bounded accumulation mechanism holds. Okay, that's the background. It was really meant for people who weren't here on Tuesday, but hopefully it was helpful to some of you who were. Okay, so now let's turn to the first topic, which is to use variance and covariance as signatures of neural computation. So what I'm going to do is I'm going to introduce a metric that I hope will be useful to many of you, even if you don't want to study decision making. But of course, the reason that we developed it is because we wanted to apply it to our data. So I'm going to do two things with this part of the talk. So I'm going to apply, I'm going to just unite two very simple ideas. One is the theory of doubly stochastic point processes, and the other is the laws of total variance and total covariance. Okay? And it's a really simple idea, but it turns out to be useful. So now let me just remind you, or tell you if you don't know this, that when you observe a random variable that is dependent on some other hidden variable, in this case we're observing x, and it's dependent on y, that if we make a measurement of the total variance on x, we can divide that into two components. One is what's something we can call the variance of a conditional expectation. That is the variance of the expectation of x if only we knew y. Okay, and the other one is the expectation of a conditional variance. Okay, now you actually do something like this every day that you do least squares regression. Okay, one of these is the variance of the residuals, and the other is the variance of the expectations from the regression. Okay, so this is even though we don't tend to think about it this way often, it ought to be in your comfort zone. Now, when we apply this to doubly stochastic point processes, what we're thinking of now is that X now might be the spike counts we get from a neuron in some short window of time. And in case I forget to say it, I'm always going to look at windows that are about 60 milliseconds wide, because that's about the shortest amount of time that some of the assumptions that I'm going to exercise are even close to valid. They're actually not completely valid. But I want to have some temporal resolution, because I'm going to want to see how this quantity changes in time. I haven't said which quantity yet, but I will. So the idea is that we can think about X now as a spike count, which I'll represent as uppercase N for number of spikes. We can sort of think about Y in this expression as rate, as if the neuron is being commanded to give you some kind of output, and it can't give you that output exactly. It renders that command through a point process that is itself going to produce some variability. And that's the basic idea behind a doubly stochastic point process. So now we're saying the total measured variance of the spike count is something I'll call the variance of the conditional expectation. In other slides it'll be var-CE instead of VCE, sorry. And plus a variance that's just due to the point process. Now, we don't really believe that neurons get a command signal and then render it as a spike, as a point process. I mean, it's a lot of times when we make models, we often do that. We often do exactly that. We say, here's the result of the computation, but I want to make it look like a neuron, so I render this rate, maybe time-varying rate, with spikes. But we don't really believe neurons do that. Nonetheless, it's a useful contrivance, because we're very interested, trial to trial, in how this kind of a quantity varies. You could sort of think of this as representing the neural computation, and this is the stuff we want to explain away. You know, when we infer neural computation from looking at average spiking rate over many trials, that's sort of what we're doing. We might see some interesting dynamics in the firing rate, and we kind of want to look past the variability of the spiking. And this is what we're going to do, but now so that we can look at the variance. So what we'd really like to do is look at this term and get rid of this term. So how can we do that? Well, it turns out we can make an assumption that is incorrect, but I would argue incorrect in kind of a benign way. We can assume that the rendering of the spikes is via something I'll call a generalized renewal process. Now, technically, a renewal is a stochastic point process where all the intervals are independent and identically distributed, okay? Which means the rate can't change, okay? But we're going to assume that the rates change, and when they change, they effectively scale time, okay? And all that really means is that if I were to rescale time, I basically just have the same point process, okay? And so, for example, a non-stationary Poisson process would have a variance that was equal to its mean, period. End of story. The rates can change, but if it was a random process, a Poisson process, that was generating spikes with varying rate, okay, but the rate was changing from moment to moment, we would be justified in assuming that the variance of the counts produced by such a thing would be not just simply proportional to the mean of the count, n bar here, but where this constant proportionality phi is 1. In general, for renewals in general, we don't know what a neuron really is. We'll say we don't know phi. We're going to have to estimate it. Yeah.
This is the fluctuations in the expectation.
This is the fluctuation.
The left-hand side.
This side?
Yeah.
No. This is the total. No, sorry. I flipped these around. This is the total variance. That corresponds to this term. I've used S for the estimator of these quantities. Okay. In order to isolate the variance of a conditional expectation, I need to take what I measure, the total variance, and subtract an estimate of the point process variance. If this were a non-stationary Poisson process, I would simply subtract out the mean of the counts. I'm saying we don't really know what kind of a process this is, okay?
But stationarity is within the short time.
That's not necessary either. Okay, let me say where some of the assumptions are immediately going to fail. If we have this thing that I'm calling a generalized renewal, okay, that has lots of different names, okay, but in any case, I'll just use the term renewal, even though it's technically not correct. That if you have enough counts, you need to have a window of length on order expectation of intervals of being about 3 events or more. Then, if that's true, this holds that what really holds is that the coefficient of variation of the interspike interval distribution, which is the signature of this particular stochastic process, if you square that, then you will have this variance to mean ratio. Anyway, it doesn't matter so much. But the constant proportionality argument it rests on this renewal assumption. Okay. Now, by the way, the evidence that neurons in the brain are renewal is actually, there is no good evidence for it, except the fact that people do tend to measure a constant ratio of variance to mean under a variety of conditions. If you change the contrast, if you change the attention state, and you change the neuron's firing rate from state to state, you get a pretty roughly the same ratio of variance to mean. Some people fit it with the power law and so forth. The argument against the renewal, it turns out, I think, will be explained by much more simply than it usually is. Okay, there are oftentimes appeals to interesting higher order statistics, but I think what you're going to see is that the real reason why is probably because there is variance from trial to trial in the conditional expectation. It's a very simple argument. Anyway, I can't prove it, but I'm dwelling on this because it's the weakness in the theory. We need to know what phi is, and we never will know. Okay? Because if it were, suppose I was to say to you, I think what it is, it's the variance to mean ratio, what people call the Fano factor. That's stating, that's implicitly, that I believe that there is no, if that is true, then that implies that there is no variance trial to trial in the conditional expectation. Okay? That's what that statement would be. So I don't know what this is. I do know, however, that this term can never be negative. So that gives me a bound. So we have some tricks, and I'll come back to what some of these tricks are for estimating phi. Okay? But let me just make sure that you have an intuition for this quantity by just making some sort of teaching demonstration. So suppose we had a process that was truly stationary, boring process, that every trial we would get whatever this is, 22 or 25 spikes per second, okay? And so here might be 10 trials of random spikes, and these are I'm generating Poisson, in this case, a stationary Poisson spike trains, okay? If we go through our calculations, what we get is that the variance of the conditional expectation is 0. Now, the total variance, of course, is equal to, in any given window, is equal to the expectation of the counts in that window, which is just the length of the window in time times 25 spikes per second, okay? Okay, but the variance of the conditional expectation is 0, okay? That's what by design. If, on the other hand, from trial to trial, we vary the firing rate, the driving command, okay, then this picks up what what that variance is. You're looking at a distribution now of expectation in the rates, and this is what our quantity will pick up. Okay, and this will hold under. I don't know why this thing isn't. This will also hold under non-stationary rate. I've done the same thing from trial to trial. I've just added the same offsets here as to here, but now I've happened to add those offsets to ramps. Okay. Okay, and you can see that in both of these cases, the red and this black, they're picking up non-zero variance of conditional expectation. Okay, they're telling us something that we can kind of see. Okay, perhaps a little bit more interesting is suppose the from moment to moment, say in every 10 milliseconds, we take a new random perturbation. So we have an expectation, it's this purple line, but we happen to get variation in what the driving command of the neuron from trial to trial, but also a different number every 10 milliseconds. Well, in a 60 millisecond window, we kind of get a little bit of benefit of signal averaging of our 6 independent samples of noise, but in the end, what we return here is basically a number that is another non-zero variance of conditional expectation. Okay, think of it as the variance in the driving command from trial to trial. Okay, here's the much more interesting example and why we developed the metric in the first place. So consider diffusion. Now with diffusion, the average is another ramp. It looks just like this. It looks just like this. But what we think is going on is actually that on any given trial, the firing rates are really a rendering of any one of these random paths. Okay, well, if that's the case, now the variance of the expectation should be aligned because we're accumulating variance as a function of time. We're adding independent random numbers. That's why we developed this. This looks quite different from this, okay? And I'm going to show you in a minute that this is in the data. Okay, so let me just make sure we're on the same page. That last thing I just showed you is, I've been working on this for years and years, trying to figure out whether from a series of spikes, whether or not I'm looking at something that is a step function, that has steps at different times, ramps that just have, rendered by random firing rates, or my preferred interpretation that on any given trial I'm actually looking at something I can't know, which is a random diffusion path, of which I get to sample just a spike here and there. Okay? How would I know it? Well, this is what this metric is going to show that to us. Okay, so here's what data look like. This happens to be data from, I can't remember if it's the 2 or the 4 choice task, but I'm going to compare both. In 3 analyses, epochs. In this first one, which we didn't talk about on Tuesday, when the targets come on, those 2 choice targets, okay, there's a big response because one of those targets is in the response field of the neuron. Bam. Okay, and then this period of time after that dip, when there's the period of time where I'll call it decision formation period. It begins about 190 milliseconds after onset of the random dot motion that we see this divergence of the activity according to the motion strength and the direction. And then at the end of the trial, around the time of the saccade, which I was, we've hypothesized or really deduced from the data, is there's a sign of some kind of a bound, okay, some kind of a stopping point. Okay, so let's look at each of these epochs in turn. So if we look at the period of time when we, right after we turn on the target, I'm not going to show you every aspect of the data, just focusing on the interesting features that we've learned from this by applying this metric. So here's just firing rate now. I'm not showing you the variance plots yet. And what it shows is that when we show that when the monkey is in the sees a trial where there's only 2 targets on the screen, he says, "Oh, I'm in the 2 choice task." The responses are a little higher than when he's in the 4 choice task. And this has been interpreted as some kind of representation of uncertainty. That is, the greater the uncertainty, the lower the firing rate. Okay, and this reproduces really a result from Michel Basso and Bob Wertz in the Superior Colliculus. Okay. And so let's look at what happens when we look at the variance. You notice that the blue curve here, which is 2 choice, is now below the red curve. That's interesting. This is now, I'm looking at this interesting quantity, the variance of the conditional expectation. And I guess I should have said that the way we estimate phi, before I really get too deep into this, is we say, look, the variance can never be the negative. No variance term can be. So we subtract off, we make phi a value so that we never get a negative variance of conditional expectation. The maximum phi that allows that. There's another limitation, which is that, as you see in a moment, I'm going to calculate a covariance of conditional expectations, and I must have a positive definite covariance matrix. Okay, so that turns out to be useful too. So we have certain kinds of constraints that bound our estimate of phi.
Why not maximum likelihood without making?
We can't do that because, think about it, oftentimes the data, we do not know that there would ever be a condition where the variance of conditional expectation ever goes to 0. We can't know what it is. Okay, so there's nothing really to fit there. We're wide open to finding better ways to do this, to be honest. It is the weakness. And an assumption we make is that once we've estimated phi for the neuron, we're going to use it throughout the entire trial. So we're making the assumption that the neuron's not in some bursty state in some point and a less bursty state in another. That's probably not always true. We don't see any evidence for bursty modes in our data, but we could miss it easily. We're just looking at spikes, right? So these are the weaknesses in the theory, but hopefully we can get past it. I mean, the bottom line is that what we do, and I don't know if I'll do it on any slides here, is that any interesting conclusion we make, we make sure it's robust, misestimation of phi. Yes?
I'm just confused. Is the noise that is driving the diffusion on a single trial related to the randomness of your random dot stimulus, or is there an additional noise source?
It's related to the random dot stimulus, and we can look at that by controlling it. But it's also related to there's additional sources. We think in MT. So if you change the if you remove the variance in the random dot stimulus, okay, there's still some variance trial to trial because the monkey might not fixate the same way or whatever it's going to be, it's a different attention state, whatever. But if you do that, you do reduce the variance. I used to think we didn't, but I think we made a mistake in that paper. But you reduce it to such a point, for example, the coefficient of variation of the reaction time distribution, okay, reduces by about 30%. So the variation in the stimulus does account for variation in the behavior and, I think, variance in the neural response. But the actual quantitative, if I said what percentage of the total variance is due to the stimulus, I'm guessing it's on order half. But if it was 2/3 or 1/3, I could, it's possible. So
in this experiment, trial to trial, you change the stimulus? Or
yes, this experiment, trial to trial, we change the stimulus. Yes. Yeah. Okay. We do some trials where we repeat the exact same random number seed, the exact same movies, but I'm not showing you that. Okay, but notice, I had forgotten to tell you how we estimate this value phi, okay? But so now we're plotting this variance of conditional expectation. In other words, sort of the trial-to-trial variability in the command to the neuron. And you notice that although the responses are lower on forward choice, in terms of firing rate, they're higher in terms of the variance of conditional expectation. So what could explain that? Well, this is a signature of a mixture of states. So the forward choice, when we look at these data, we'd say, well, there's 4 things on the screen, so maybe there's some surround inhibition, or maybe there's a division of attention, or whatever it is, something like turning the contrast down in the visual cortex. No, it's not just that anyway. It's that there must be some mixture of a variety of states, because otherwise we wouldn't see this increase in the variance. Typically, if you lower the response, you get a lower variance, right? Variance usually scales with neural response, okay? So that's the first thing we've learned from this. I think it's interesting. That you can pluck out a mixture of states. Okay, so now let's look at this motion, the motion viewing period, the decision formation period. And what we see there is, we'll look at a couple of epochs. And what we see is that, actually what we're looking at here is, if I remember right, I think this is the 0% coherent motion for one neuron, and then this is population data comparing 2 and 4 choice. And by the way, since we're doing variance measures, we can combine data across many different conditions by only looking at residuals, right? So it's a pretty powerful tool in that way. And what you see is after this dip, during this period where things seem to be rising, okay, in the data, you saw a much more beautiful rendering of that in the data set I showed you on Tuesday, and actually just a few minutes ago. But what you see is that the variance is increasing linearly. And interestingly, it increases at almost identical rates for 2 and 4 choice. Okay, as if whatever quantities are being accumulated, and they're probably different in the 2 choice versus a 4 choice test, the variance that's being accumulated is very similar. Okay, but this linear rise in variance, for me, that was just a really fun thing to see, because it is a signature. It's the kind of thing that would arise from something that was trying in its rate, effectively, to render, trying to render a quantity that is itself the accumulation of independent random numbers. Okay.
Are numbers on the y-axis, or?
They're not worth taking seriously. They're the same as we saw before, whatever.
No, it's an evidence.
These values. But you can't take them too seriously, because that depends on phi. Okay? So if I change phi, I don't change this. I'm always going to get this linear rise over a whole wide range of choices of phi, but I'm going to get different numbers. Yes?
It's an evidence for a quarter,
Excuse me?
With 4 options, it's an evidence for a quarter of motion, not a plane, but a quarter of.
Well, what it really looks like is evidence of your preferred motion against all the others, but since 2 are orthogonal, they don't matter as much. Okay. But the monkey begins his accumulation from a lower state. You see this? The bound is actually at the same value, so it is at the same level, okay, in the 2 and the 4 choice. So effectively, that's like raising the bound. It's just that the way the brain does it is by starting the accumulation at a lower state, okay? And yet we see this consistency. Okay. So now I want to turn to the second metric, which is we're just simply going to apply the law of total covariance to spike trains. And I'm going to be looking only, I'm not recording from more than one neuron here, so we're going to do covariance in time, so really autocovariance. Okay? So we're going to look at the spike counts in epoch I and look at the covariance of that with the spike count from the same neuron in the same trial in epoch J. Okay? So the law of total covariance is written here. Again, there's a covariance of a conditional expectation. Okay? It's how the expectation of the count would covary if I knew the 2 rates that were driving those counts. And then there's the expectation of the conditional covariance, which is like the point process variance. Now, applying the theory of doubly stochastic point processes, according to that, if I'm looking at I not equal to J, okay, right? Then if I is not equal to J, then if I knew the 2 rates, then once I know the rates, there should be no covariance here. Okay? If I know the 2 rates and the only variability is due to rendering those 2 rates, once I know those rates.
Are you assuming the Poisson?
No, it doesn't matter. I'm just going to assume that I know. Look what this term is.
It's a stationary renewal process. You have correlation in time for the spike count.
Right. But what I'm going to do is I'm going to divide the total variance up into the component that is, let's think of what these terms are. So this is an expectation. The reason it's an expectation, I'm going to have different rates on any given trial. Nonetheless, once I tell you the rate in epoch I, and once I tell you the rate in epoch J, then the only variance we're talking about is just the rendering of those 2 rates. And if there are different points in time, they're not going to covary by this idea. I'm making the assumption that all of the variance, all of the covariance in time is going to be due to the rate. Now, that may not be true, okay? But I think this is going to be a really important point, especially to many of you here, because you'll see that the motivation for some of this is it's very closely related to the joint BSTH.
Stationary process.
Yeah.
So rates are, there is no fluctuations in rate.
If it's stationary.
Stationary but renewal, not Poisson.
Stationary but renewal.
Renewal.
Yeah, sure.
Would there be a correlation in time in spike count?
No. Well, stationary. Then yes, of course. If it's stationary, it's kind of the.
Poisson will not have, by definition, there are no correlations in time, but only Poisson.
Wait, okay, Tom, we're talking about 2 different things here. Why don't you wait till I get to the end of this thing and see if this still makes sense to you. I'm telling you that if when you measure the counts in 2 different epochs, and I'm suggesting to you that if you knew the rates in these 2 different epochs, and the only thing contributing to the variance was the rendering of those 2 rates, then there should be no variance. This term becomes 0. Okay?
The higher order moments should not. Right.
We're ignoring that. Yeah, right.
Just ignore it. It's not,
right.
It doesn't
Yeah.
depend.
That's right. But we're saying that this is if we apply this theory of doubly stochastic point processes, okay? It's a strong assumption. Okay, so what it says is that what that means is that for the off-diagonal terms of the covariance matrix, the measured covariance is the covariance of the conditional expectation. This is by assumption. Okay, this is by I'm saying that when I see covariance in the counts, okay, and they're in different epochs, I'm going to say that the rates covaried and drove the counts. Okay, and if that's not, and of course on the main diagonal, that's not going to be true because the total variance once again is the sum of a variance of conditional expectation and this point process variance, the thing I'm going to estimate by phi times n bar. Okay. So is everyone with me on that? I mean, I'm not saying this is like, this is true no matter what. The fact that this is 0 is not a fact, it's a statement of a theory. Okay, I'm saying that if we are generating spikes whose only randomness is due to a point process that is rendering rate in that epoch and is not affected by anything outside that epoch, then there will be independence in this term. That's all.
So it's a rate code assumption.
It's a rate code, yeah, absolutely.
Don't mention anything but the rate.
Well, I'm not saying that. I don't know, but I'm just saying. But this, let's just say.
Is it just a Poisson?
What? No, we're
It's
not.
a Poisson assumption?
It's not a Poisson assumption.
Two epochs are dependent?
No, it's
Inhomogeneous Poisson.
inhomogeneous renewal. Doesn't have to be
What
Poisson.
are the lambdas? What do you mean by
Lambdas are rates. They're really rate as a function of time within the epoch. Okay.
So a stationary renewal process will not have a constant lambda in your definition.
Well, I'm using this renewal using renewal in this sense of sort of the generalized renewal. We can scale time.
Simple renewal.
Simple renewal. What about it?
Will have a fixed rate in your language or not?
Simple renewal does have a fixed rate. Yes, it has to.
But then there are correlations in time. So, okay, we can discuss later. Okay, let's discuss it.
Yeah, I mean, I know we're missing each other because this is really a simple idea. The only place where this breaks down is that if you have neighboring epochs, okay, that could share an interspike interval, then it's technically not true that if I tell you the rate in one and the rate in the other, that there would be any that I could state with certainty that this is zero. But other than that, this is pretty trivial. Okay, so let's apply this now to this diffusion, to the decision process. We have this long epoch we can look at. And remember, we think that in time, which I'm plotting here and here on the outside of this is the covariance of the conditional expectation matrix, okay, rendered as a heat plot. Remember, the beginning of decision formation is in the epoch beginning just before 200 milliseconds. So these are 60 millisecond wide bins, okay? And this main diagonal would be is going to all be ones because we're going to convert this covariance of conditional expectation to a correlation of conditional expectation by the usual move, dividing by sigma I, sigma j. And so basically the steps are as follows. Measure the raw covariance, okay? Do nothing else to the off-diagonal terms. That is the covariance of the conditional expectation, okay, by assumption. And in the main diagonal, replace that with the variance of the conditional expectation. Subtract out the point process variance. Okay, that's all you have to do. It's pretty trivial, okay? And now make sure that you don't violate R values that exceed -1 to +1, and make sure you have a positive semi-definite matrix. End of story, okay? And and what you see is a reasonable signature of diffusion. There are two things to look at in here. One is that if we start with the very first epoch and look at its correlation with all subsequent epochs, I'll just plot this upper row now, you see this hyperbolic decline in correlation, okay, which is what you expect. And the other thing you see is that as time goes on, if we look at juxtadiagonal terms, they're growing. There's a kind of a moving out in the correlation. Why is that? Because as these paths diverge, if you were like above the mean, as you go further and further away, you're going to stay above the mean. Okay, that's the intuition on that. So those are the sort of two features of correlation in a time series governed by diffusion. Okay, and we see that's the data. Okay, so that's kind of nice, and we can use that now to compare with a variety of alternative models. Okay, so this is what diffusion achieves. Okay. A drift diffusion, we're not putting in bounds, so this is not going to be exactly like our data, but nonetheless, we see a linear rise in the variance of conditional expectation in simulation, and we see this kind of a feature. The data is shown in blue here, or black, I can't remember now. One of these is the prediction of the model. Okay, the data are blue because that's going to show up in all the graphs. Here's an interesting alternative. Many people believe that the same expectation, the same average firing rate, say as a function of time, this ramp, could have been caused by variable rate of rise, that is ramps on any given trial. It's just that the rate of rise was different from trial to trial. You can take such a model and find a way to explain a lot of our data with it. It's often known as the later model for linear accumulation to threshold with ergodic rate. That's after Roger Carpenter. But you can see that this produces, it turns out, a quadratic rise. Analytically, this is simulation, a quadratic rise in the variance of conditional expectation, and a flat and very high autocorrelation of conditional expectation. It's clearly nothing like the data. Here's another example. This is sometimes called time-dependent scaling, either an increase in attention in time or just some time function. Paul Chiswick published a model like that to explain our data, actually. And you can easily explain the mean rates with it. In fact, we use parameters that would do a better job of explaining our data than Paul managed to pull off in his paper. But nonetheless, again, you get a quadratic rise, roughly, of the variance of conditional expectation, but you get really no correlation of conditional expectation. So it's a very striking difference between diffusion and these two models. And then here's some models that do work. So Alex Pouget's probabilistic population code works. The reason it works so well is because all it is diffusion in the end. He's just adding random numbers, so it has the same kind of feature if you were to look at single neurons. And here's Xiaojing Wang's attractor model. There are many models like this, all going back really to Usher and McClellan. And these models, I think, are interesting because we collaborate with Xiaojing. He can manage to tweak enough things to make the data look a lot like make the model look a lot like the data. But in my view, this is kind of ultimately going to be a killer for attractor models because what's really kind of nice about this is that you can see. For those of you who don't know about these models, they make a very beautiful. They do a very beautiful thing in one way, which I think was going to turn out to be wrong. They couple integration with decision making. So they couple recurrent excitation in an appropriately balanced and stable way to give you integration with competition so that there's an instability and one accumulator wins over the other. Okay? And what you see in those kinds of models is you see in these kinds of graphs evidence for a mixture of states and for both the nonlinear dynamics of sort of flying into an attractor basin, and also an epoch in which the dynamics are more diffusion-like, but they're extremely delicate. And so, but in this particular graph, they're reasonably close. I'm very disappointed with that because I actually think I'm also collaborating with Eric Shea Brown, who's also, we had a poster at Neuroscience this year that showed just how incredibly brittle these attractor dynamics are to this, which would be obvious to any of you who work with them. Okay, so now let's look at the final phase. Near the time of the saccade, this is pretty trivial. All it shows is that if we look at the trials that are going to end with an eye movement to the target in the response field, we see this precipitous decline to pretty much a nadir in the variance of the conditional expectation. Again, a signature of a bound or an attractor state, if you like. And you don't see that when the monkey chooses the opposite target. Okay, you pretty much stay at this high level. Okay. And what did I want to say about that? It's coherence independent. Okay, big deal. Okay, so let me summarize this section by saying that I've introduced for you some useful tools. It sounds like there are a few skeptics in the group, but I hope that I can satisfy you on the technical points. And hopefully this will be useful to many of you in your work. It captures kind of intuitively the variation in what is being computed from trial to trial by looking at the spiking. It exposes some interesting features of computations and decision-making, integration, mixtures, termination bounds, and it's useful for distinguishing between some alternative models. The main limitation to the technique is that estimating phi is inexact and incorrect. So any conclusions are really not quantitative. That's why the labeling of the ordinate isn't terribly important, but they're qualitative. But comparisons are useful, and the dynamics, that is the functional form of the change of the variance is a variance conditional expectation as a function of time is useful. Okay, so let me turn now to the second topic because otherwise I'll run out of time. So let's talk about integration of prior probability with evidence. So these are tasks just like the ones I was showing you, we're going to restrict ourselves to 2 choices. And the way we do this is we have the monkey performing the same test we were talking about at the beginning of the lecture with left and right, say, being equally likely. And then we change to make, say, rightward more likely than left. And it takes the monkey about 150 trials before he stabilizes his performance. And I'm not going to show you those trials. But then, so now monkey's in this regime, a very stable and long regime. You see, on the order of 500 trials or so, where he's seeing more rightward motion than left. And then if we hold a cell long enough, we switch things. Okay? Now, I want to share an intuition with you that is wrong. Okay? I'm going to share a few intuitions that are wrong in order to get to what's right. So we were excited about this experiment. I mean, not just because of the whole Bayes enthusiasm, but also because we thought, as you heard in the previous lecture, that the neural responses seem to represent something like probability. Really, I was saying log odds of being correct, or log likelihood, or whatever. So we thought, okay, look, if we manipulate probability directly by changing the prior probability that motions to the right, we should be able to probably get an offset in the firing rates of these neurons, and we could then get a mapping in this experiment between firing rate and probability. Cool. Okay. Well, and you would think that the right thing to do is, if rightward is more likely than leftward, is to sort of give these rightward neurons, accumulate evidence for favor of rightward, just give it a head start towards the bound. Okay? That would be a reasonable thing to do. But that turns out to make a prediction that's easily refuted by data. So if we plot the proportion of rightward choices as a function of motion strength, strong rightward motion strength indicated by positive signs, and strong leftward motion being indicated by negative signs, so the difficult cases in this graph are in the middle, what we would expect to see from a mechanism like this is a shift of the psychometric function, a slight distortion of it too, it so happens. And if we looked at the reaction time plotted on the same axis, hello? That what we would see is that, again, because the motion is the weakest motion's in the middle, that's when the reaction times are longest, right? We would expect to see a big break between the fast reaction times associated with the preferred direction, the biased direction, rightward, and really long reaction times associated with the sort of anti-biased direction, the rare direction that's being shown. Okay? This big break, though, is never seen in the data. What the data look like is basically a horizontal shift of both the choice function and the reaction time function. Okay, there's tiny breaks here, but for the most part, if you look at these data, it looks like someone just changed the motion strength. Okay, it looks like what we get if we microstimulate in area MT. It's like we added a little bit of extra, if the bias is in the favor of rightward, then it's like we added a little bit of extra rightward motion. Okay, this is data from monkeys, and we see the same thing in humans. Yeah.
The proportion right is okay. So the problem is the reaction time.
That's right. Yeah, well, it's not really okay. These are really pure shifts of functions, whereas there's a distortion of the shape of the reaction of that function too. But that's subtle.
Okay. You get this asymmetry between the probability to the right and the left because prior probability of 0.2 to the right is opposed to 0.8 to the left. Right? So how come you get this asymmetry between the blue and the red
here?
graph? Yeah.
I don't. There's probably non-decision time or something. The monkey's just faster on average when he makes a rightward eye movement than the left in this experiment. It's not a big effect.
It's one experiment.
No, this is an average of many experiments, actually. Yeah.
And I don't know many monkeys.
This is one monkey, I think. I don't remember actually for this graph, to be honest.
How come left is longer even in priors?
That's what Udi's asking. Yeah. That's a small effect, okay? We're going to look at some pretty big effects. Let's see if that holds up, actually. It's something I haven't really noticed. Okay, so now I'm going to give you another intuition. Again, it's going to be wrong, but it's closer to right, okay? I've already given it to you. If you look at a function that looks like this, and now I'm doing a cartoon version and you'd say, well, it's like someone changed the motion strength. Okay, so what would that mean in this bounded evidence accumulation model? Well, that's like someone changed the drift rate. Okay, like the momentary evidence has a higher mean, so the rate of the deterministic component of this drift diffusion is higher. Okay, and if that's true, that's kind of weird. It's not going to be exactly true, but it's going to be close. And this thing is going to be true, is that it suggests that prior probability, which is constant across the trials, constant across 500 of these trials, plus the 200 before, is represented dynamically as a function of decision time. Ooh, that's beginning to sound a little bit like the result we had in the confidence experiment. So here's what we think is really going on. If we plot the proportion correct as a function of decision time, okay, so we infer decision time by, this is a theoretical graph. We fit the monkey's data, or the human's data, okay, and we actually do a fit with collapsing bounds, and we get the whole distribution of the reaction times, conditional on choice, whatever it is. But we get the expectation of being correct as a function of decision time, okay, backing out the non-decision time and so forth. I won't get too technical. But you see that what you notice is that the proportion correct is very high at short times, and it declines at long times. Why is that? Because we're very fast when the motion's strong, and we won't make errors. And when the motion's weaker, we do make more errors. Now remember, for those of you that are savvy about sequential probability ratio tests and these classic results, the time-dependent accuracy function for any one coherence is flat, okay? If the bounds were flat, okay? If the bounds are collapsing, that's not true, okay? But even if the bounds are flat, because we have a mixture of motion strengths, as time goes on, it's increasingly likely we're working with a weaker motion strength, okay? Okay, and that's this thing, this regularity that was exploited to compute the posterior odds of being correct, okay? But now the argument is that we can from this observation figure out what the dynamic signal should be to implement the prior. And it goes like this. I'm going to present it to you in the form of an algorithm. Okay? Fit the monkey's data or the human's data under neutral priors. Okay? Bound height, some term that gives you the conversion from motion strength to signal to noise. Okay? And in order to explain, to get back the observed time-dependent accuracy function. And what we'll do then is we're going to infer, we're going to figure out what a bias, a time-dependent bias signal is to add to this accumulation. Okay? That's what we're going to do. How are we going to get that? Well, I guess I'm going to show you a result before I tell you exactly how we're going to get it. I'm going to tell you, in a minute, I'm going to tell you how we get it. And when I do, I'm going to be able to predict the change in performance of two human subjects and the monkeys. This is grouped monkeys. Okay, that's what we're going to be able to do. So these are going to be predictions, and the circles are data. Okay, so how do we do it? I've skipped something. Oh yeah, I see. Yeah. Okay, let me just explain how we do it. Sorry, my bad. We take the time-dependent accuracy function, and we say, look, at the bound, this equals the log of the odds of being correct. That is just a re-expression of the time-dependent accuracy function. And then we make an assumption that's incorrect, but is approximately true. That the log of the odds of being correct is a linear function of the value of the decision variable. Fine. The prior probability is 0.8, say, in favor of right. Right? So the log of the prior odds is the log of 0.8 divided by 0.2. In other words, the log of 4. We say, what's the fraction of the log posterior odds of being correct? Okay? Take that number, the fraction of the bound, that's our dynamic bias signal. That's the bias signal at any moment in time. Okay? So I've just given you the recipe for taking a subject's performance under neutral priors and inferring what they ought to add in to their decision variable in order to realize the prior. And that's what these dashed curves are. And I said they were predictions, but that's actually an exaggeration. There's one degree of freedom, is that we didn't assume that the subjects or the monkeys knew exactly what the prior was. Okay, so that there's one fitted term. So the fitted prior is not 0.8, but some number near it, it turns out. Okay. So these are, consider these fits. They're one degree of freedom fits that explain the, reasonably well anyway, the choice and the reaction time data for humans and monkeys. It's going to get better than that in a second. I'll make a real prediction. Okay, so now we have two tests of this idea. The first is in humans. What we do is we change the speed accuracy regime. So in this case, what we did is we changed them from a high accuracy, therefore low speed regime, to a faster, therefore less accurate regime. Okay? So you can see they're faster now. The reaction times are, down near 600, 700 milliseconds or so at max. Okay, and they're a little bit less accurate. You can tell that because if I show you in gray lines or in black lines, I'm show you where they were when they were. This is when they were highly accurate and slow. You can see they were super slow. I'm superimposing the reaction time data and the choice data on the same graphs. And by the way, accuracy here, I mean sensitivity is the slope of this curve. Okay, right? It's the rate of change of the choices as a function of changing the motion strength. Okay, so this is just to tell you that they're in a different regime, a strikingly different regime. They're faster and less accurate here. And indeed, if we look now at their time-dependent accuracy function, it's very different than it was in the first regime I showed you. Okay, so if that's so, what we do now is we apply the same recipe. We say, okay, from this we can infer what the meaning of the bound, what the meaning of the decision variable was at the bound. We'll apply a linear approximation and say that space, the value of the decision variable, is proportional to the log odds of being correct, a time-dependent quantity, and we'll take the log prior odds, which is the log of 4, and we'll just express it as a fraction of the bounds, now interpreted as log posterior odds of being correct. Okay, there's no way you're going to follow every one of these steps, but you get the gist of it. Okay, we're saying that the monkey has an implicit knowledge of his own decision criterion in units of being correct or not correct. It's the exact same idea that was in the confidence experiment I showed you yesterday. The idea being that the brain forms an association between the state of its decision-making machinery, say firing rates and LIP, and whether it will be correct or not. Okay? And with that, there's an obvious weighting of the prior. And so now we can make a complete prediction, because whatever we think the human or the monkey estimated 0.8 to be, we'll use that number here, and we'll predict the performance, and hooray, and it turns out these predictions are pretty good. They're not perfect. You can see lots of violations here and here in particular, but again, I think it's pretty unusual. There's a very, very, very rich data set, and with no degrees of freedom, we're able to basically rise to the challenge of saying, okay, we made the prior probability 0.8 instead of 0.5 in favor of rightward. How much is a human, how much is a monkey going to change their choices and their reaction times? Okay, we don't get it exactly right, but it's pretty close. The second test is to look at the neurophysiology, and now this is where I really did write it out as a recipe. I don't have time to bring you through this calculation in detail, but basically you take the neural firing rates and you just measure that as a function of motion coherence, okay, under the neutral priors and under the bias priors, okay? And then what you do is you work out what the buildup rates would be, and you look under each case. These are leftward motions, these are rightward motions. This is when the prior favors rightward, and here where the prior favors leftward. And these are just average buildup rates that we can estimate. And we look at the difference in these rate of changes, and basically what we're going to do then is approximate in a discrete way what we think the first derivative is of this dynamic bias signal, because the trick here is that different coherences are contributing more trials. All coherences are contributing all their trials at time 0, but as time goes by, the easier trials are dropping out of the mix. So from that, we're able to estimate what the rate of change is. This would be a perfect line. It's a minor departure from a line in this case, and it's this function here. Fine. So we get an estimate from the buildup rates across many trials of what we think this dynamic bias signal is. There it is. Okay, this is just the solution of this is just integrating this approximation to the first derivative of this expression and taking this offset from the measurements themselves. And then what we do is we just add this back to the behavior that we measured under the neutral prior. And again, we're in a place where we now just take a look and see what kinds of predictions do we make for the monkey's behavior. Okay, and these dashed curves are the predictions by just taking this neural response, basically the difference in the firing rates under neutral and non-neutral priors, and adding them back to the model that fit the data under the neutral priors, which are the solid symbols and the black curves. Okay, so we're pretty excited about this. With the monkeys, of course, we can use the neurophysiology to infer this dynamic bias signal because we can measure it. And with the humans, we can actually manipulate the speed-accuracy trade-off and see that we just didn't get lucky to come close to the shifts in the choice functions and the reaction time functions, but rather there's some principle here at play. So the conclusions from this section of the talk, and this will be the final slide, is that bounded evidence accumulation explains some decisions. I gave you examples of that on Tuesday, and I've expanded on that here by, in part one of the talk, showing you that there's more evidence for this diffusion mechanism than one could have gleaned from average firing rates. And in the second part of the talk, extending the mechanism to explain the incorporation of prior probability. Neurons in parietal cortex represent graded quantities. I think I made that point strongly in the first lecture with the shapes task, that probabilistic classification task, but here with the accumulation of evidence from the visual cortex, the direction-selected neurons, and that neural computation in association cortex might be articulated in the language of probability theory. I mean, I would add to that the language of probability theory combined with sequential sampling and optional stopping. Okay, which makes marginalization of nuisance parameters more difficult and makes tricks like knowing the association between the variable that's used to make a decision and the outcome of those decisions, getting reward, satisfaction of constraints, in this case just being correct or not, a very useful trick that's actually principled. And finally, I've shown you now two experiments where time matters. So the mapping of firing rate to units of probability exploits elapsed decision time. We saw that in the confidence experiment, and now we see it again in the mapping of prior probability into units of spike rate. It's a dynamic signal despite the fact that the prior is a constant in time. Okay, so I will stop there again by showing you pictures of people who actually do the work, and thank my supporters and especially the monkeys for participating.